today is a summary of these two recent papers. We also earlier, before these two, we put up some paper on arXiv in collaboration with Sergei Bukov, Liu, and Professor Yao, which we actually originally studied this problem using gauge theory and gauge deductions related to the three-fold geometry, the two-fold geometry. Okay. So let me give you somewhat background on Hilbert schemes. These are algebraic spaces which were first constructed by Alexander Grothendieck. He was interested in transcribing closed subschemes of projective space. And he constructed this Hooke scheme in frame 4, and Hilbert schemes are particular special case of Hooke schemes. After that, Hilbert schemes became quite fundamental ingredient in modern algebraic geometry. Many people worked on them, and especially Hilbert's curves on points on surfaces and threefolds became somehow focus of attention of many mathematicians and physicists. And as you will see today, these are related to physics as well. Okay, so many people, more contemporary mathematicians, worked on these, and just show you kind of a pictorial history. So this is Robin Hartshorne, who studied connectedness of Hilbert schemes of curves, for example. This is a picture of Nitin Nitzur. He also worked on constructional aspects of Hilbert schemes and Hooke schemes and so on. This is a picture of John Xavier. He studied combinatorics of these Hilbert schemes. This one, some of these pictures actually, they will come up later in my talk. This is a picture of Manfred Len, and he studied cohomology of Hilbert schemes. This is one of my favorites, Ludwig Goethe. He calculated Secchi numbers of Hilbert schemes of points on algebraic surfaces, and he constructed generating series of these numbers, and he proved modularity properties of these spaces. Of course, Richard Thomas, in the context of Downton-Thomas theory, I mean, he studied intersection numbers of moduli of sheaves, and this was something, some new fields he introduced in order to kind of answer certain questions about Gromov-Witten theory. So if you ask your sheaves to be ideal sheaves of some spaces of some three-fold that they curve, your moduli is indeed Hilbert scheme of curves on the three-fold. So he studied Hilbert schemes too, and Andrei Bukov, who did plenty of work on Hilbert schemes of surfaces and three-folds, using algebraic geometry and representation theory. This is of course a picture of Rahul Pandey, who also did plenty of work on this and many results, and he also collaborated with Andre and Richard Thomas, and of course, how can I not mention Professor Downton. Okay, so this is I mean, there are many others which I just mentioned a few here as an example. So let's discuss some background. Let S be a non-singular projective surface over complex numbers. So two complex dimensional smooth manifold. One of the objects we're going to study is the Hilbert small point. So for any non-negative integers, Hilbert small points of the moduli space are parameterizing things like this. So calculations of points on the algebraic surface. And in order to parameterize these, you need to kind of give the total sum of how many points you have, and you need to count points with their theoretical multiplicity. So the total sum of multiplicities is what we call length. So you fix an integer, and there's a moduli space that parameterizes these, and that's the Hilbert small point. This is a notation for it. Next one is Hilbert scheme of divisors on the algebraic surface. These are like naked curves, if you like. These are divisors, and to parameterize them, you need to fix their cohomology quantity. You fix some elements of second cohomology of the surface with integral coefficients, such that the honors is effective, and the Hilbert scheme of curves parameterizes these divisors with that class. The next object of the study is kind of decorated with points and curves. So if you like, this is the moduli space or the Hilbert scheme of curves and points. Algebraic geometer, instead of saying curves and points, calls them non-pure one-dimensional subschemes. Pure one-dimensional subschemes means just a divisor. Non-pure means it could be a divisor together with zero-dimensional subspace attached to it. And of course for this, you need to fix the number of points, which is 10, and the cohomology class of the divisor. So that's the notation. Okay, and somehow, in order to parameterize these, you can, I mean, in algebraic geometry, parameterize these, it's often calculated with a sheet. You can look at functions vanishing on this configuration of points and curves. These are modules over the local coordinate ring of this linear surface, and they make an ideal. It's called an ideal sheet. And second first class of the ideal sheet gives you the number of points, and then this divisor has the class data, and I call this whole configuration Z prime zero-dimensional piece plus the divisor. Okay, so this is our notation. Now some remarks about these spaces. The Hilbert small point, if the surface is smooth, the Hilbert small point itself is smooth. So it's a variety, the smooth variety of dimension, complex dimension to n. Okay? The Hilbert small curve, however, if you like naked curves or Hilbert small divisors, is in general non-smooth. Unless, for any line bundle on that algebraic surface, whose first class is equal to our given fixed cohomology class, you have the vanishing condition that the cohomology is bigger than equal to 1 of that those line bundles vanish for every line bundle. The first class given by beta. Okay. And the third result, which is also kind of could be seen easily, is that Hilbert small curves of points is given as a product, isomorphic to the product of Hilbert small points and Hilbert small divisors. So this you can see in different ways. If you look at functions vanishing on a sum of union of points and curves, you can write a tensor product of functions vanishing on points, those are ideal points, and functions vanishing on divisors, and that's a line bundle, which this one transcribes. Okay, so these are the results. Now, my talk is about nested Hilbert schemes, so maybe I should tell you what the nested subscheme means. Again, it starts with this algebraic surface, and this time you're interested in nested configurations of points and curves. So I have union of a curve, naked curve, or a bunch of curves and some zero-dimensional subschemes. I call them Z prime 1, and I have another configuration, Z prime 2, and I would like them to fit inside each other as subschemes. And the whole thing has a subscheme of the algebraic surface. So how do we algebraically parameterize these? So the same way that for Hilbert scheme of points or curves, ideal sheets or deep algebraic objects, this should give you a way of parameterizing the nested Hilbert schemes could also parameterize by taking advantage of nested ideal sheets. So what does that mean? Of course, it's video we've seen that you can forget about Z prime 2 and look at functions vanishing on this configuration of points and curves. That's an ideal sheet. You can forget about Z prime 1 and look at functions vanishing on Z prime 2. That's an ideal sheet. And the fact that Z prime 2 fits inside Z prime 1 tells you that the ideal sheet of Z prime 1, and these are functions vanishing on it, fits inside ideal sheet of Z prime 2. And that gives you an injective map C, C1 in my notation. Okay. There's another way of writing this too, which I could use this third property in here that the Hilbert scheme is the product of the Hilbert small points and curves. So each one of these one-dimensional non-pure subschemes has zero-dimensional pieces. So I call one of them Z1 with length N1, Z2 with length N2. Then, of course, they have the divisorial parts as well. I call the union of them divided Z1 and Z2. And it's just the fact that, as I mentioned, the sheaf of functions vanishing on this union, Z prime 1, Z1 union Z1, can be written as a tensor product of ideal sheaf of functions vanishing on points times the functions vanishing on the Z1, and that's a line bundle. So it's an ideal sheaf, but because it's a divisor, it's also a line bundle. And same in here, I can relax I of Z prime 2 as I of Z2, the zero-dimensional piece times the line bundle. And so this map is still an injective map between the two. Now, the reason you're doing that is because now this guy being a mind bundle is an invertible sheet, and I can move it over here. So let's do that. So now I can simplify, and this injective map C1 this time can be written as ideal shape of point with an injective map into ideal shape of point on Z2 times some line bundle, which sees the difference of these two dividers. And of course, I can forget about D1 and D2, and I can find some curve, so I have class is equal to D1 minus D2, and basically just use that to transfer. So how many pieces of data I need? I need the length of Z1, and I need the length of Z2, so N1 and N2, and I need an effective curve class for C1, so and a map, an injective map to transfer this twofold nesting of one-dimensional substance. Okay? Alright, so in general, I can increase the length of nestings, I can look at the threefold nestings, I can look at the R-fold nestings, and the theory I'm talking about today is for general R. And again, I can play the same game. Each one of these things are twisted ideal sheets of points, N1, N2, all the way to an R, and divisors 1, divisor 2, divisor all the way to divisor R, and of course I can look at the difference of divisors in each level, and for R many vertices in here, I can have R minus 1 many defective curve classes. So, this is our definition of the nested Hilbert scheme. For any R bigger than or equal to 1 sequence of non-negative integers, and R minus 1 sequence of defective curve classes on the cohomology, second cohomology of the surface, the nested Hilbert scheme is sitting as a closed subscheme in the ambient product of Hilbert schemes. So what does this mean? You have R many integers and R minus 1 many curve classes, but the last sheet doesn't see any curve class data R. Now, I hope that with all of this notation and these pictures, it's obvious to you why I have one curve class less than the number of non-negative integers. But these are seeing the difference of these divisor classes. Okay, and this guy parameterizes, this is basically what I just said. So parameterizes twofolds of zero-dimensional subschemes, which are elements of this product of decimal points for N1 to N R, and R minus 1 twofolds of effective curve classes from elements of F theta 1 to F theta R minus 1. Such that the math, which I just told you how I obtain, are injected. So this is the algebraic way of constructing nested Hilbert schemes for any R. Okay, so what is it we are trying to do? We are